Hello. In this video, we are going to derive the sigma molecular orbitals of the compound diborane, B₂H6. Diborane has a very peculiar structure which is not understandable using any theories other than molecular orbital theory. So we have, along the x-axis, we have two boron atoms, which are in blue here, and this is along this particular axis is the x-axis. And then we have two bridging hydrogens, which are halfway in between each of the two boron atoms, and we've arranged them here so that they are along the z-axis. That will be vertical on our whiteboard, while the x-axis is left and right on the whiteboard. Then we have four hydrogen atoms which are all in a plane, but they're in the xy plane, so our y-axis is along the stick here, so that would be perpendicular to the whiteboard. In a sort of three-dimensional type viewing, hydrogens 5 and 6, we have this wedge to show that they're coming out of the board towards us, and the dashes show that hydrogens 3 and 4 are behind the whiteboard. Though we will not label them as such here, just to keep the amount of writing to a minimum, the s orbitals that are associated with hydrogen 1, for example, this green circle, we will consider to be the orbital s1. The green around hydrogen 2 would be s2, and so on. So it saves writing S with the same number as the hydrogen atom. But the green circle will represent the sigma bonding orbitals. So the first thing we have to do using the projection operator method is to find the linear combinations of these hydrogen group orbitals, and then we will see how they interact with the atomic orbitals on the boron atoms. The first thing that we need to do is to construct a reducible representation for this sigma bonding involved in the group hydrogen orbitals. And the way that we do that is to construct a table, and we have one column for each class in the point group. And our point group here is D2H. And the point group D2H has 8 classes. So to find the appropriate character, the number that we're going to enter underneath each column, we want to see how many of these particular orbitals do not move under the symmetry operations. Another way to think about it is we want to write down the number of orbitals that don't move when we perform a particular symmetry operation. So our first symmetry operation is E, the identity. And we see that we have 6 s orbitals on hydrogen. And since it's the identity, each of those stays exactly where they were before. So that means that 6 stay still. So our character is going to be the number 6. Next, we have the C2 around the z-axis. So the z-axis is up and down on our whiteboard. So that would flip this boron to that boron, for example. And the only orbitals that do not move are the ones that actually lie along the z-axis. So that's going to be S1 and S2. So that's 2 of the orbitals do not move. So our character is a 2. Now for the y-axis is sticking directly out of the board. So as a result of movement around the y-axis, that would rotate H1 to H2, H2 to H1, because they're going around this particular axis. It would also take H3 would move to H5, H6 would move to H4, and so on. So we would see that every single orbital would move under the C2 around the y-axis. So therefore, none of them stay still, so our character is going to be a 0. And we use a similar reasoning for rotation around the z-axis. So the z-axis is the axis that goes through the two borons. So we would notice that since the two boron atoms are along the x-axis, they are not affected by this CQ operation. But in our table, we're not counting anything with respect to the boron. We're just counting with respect to the hydrogen atoms. And we would see that when we rotate around the x-axis, H1 would move to H2, H6 would move to H3, H5 would move to H4, and so on. So all the hydrogen orbitals would move, so 0 stays still. Now, for our inversion operation, I, our center of inversion is right at this point where the x and the z axes cross. And we see that under the inversion operation, every single atom and every single orbital would move under the inversion. So therefore, none of them stay still, so our character is going to be a 0. Now we look for the xy plane. So this is the x-axis. The y axis comes out of the board. So this would be the horizontal plane going through there and then coming back up. And because of the way that we represent our hydrogen atoms, we realize that H3, H4, H5, and H6 are all in this xy plane. So therefore, those 4 atoms, since they're along the plane, are not affected by the operation. So therefore, our character is going to be a 4. Next, we have the xz plane, and that's the plane of the whiteboard, as it works out here. And we realize, for example, that H3 and H4 are behind the plane. H5 and H6 are in front of the whiteboard, so therefore they would move. But H1 and H2 are actually in the plane of the whiteboard. They're not affected by that mirror operation. So we have 2 orbitals that don't move, so our character is a 2. Last but not least, we have the YZ plane. So the YZ plane is the plane coming perpendicular to the whiteboard in this direction. We only have 2 orbitals that lie on that particular plane, H1 and H2, the S1 and S2. So since 2 do not move, our character is going to be a 2. And now we have written down our reducible representation for the sigma bonding in diborane. Our next step is to reduce this reducible representation to get a linear combination of irreducible representations. The point group D2H, the point group of diborane, is an interesting group, at least for the following reason. We notice that we have 8 classes in the point group, and that each class has one and only one symmetry operation. So that while there are 8 classes in the group, there are also 8 operations. And when we have this situation where each operation is its own class, this tells us that we have an abelian group, that the order of operations doesn't make a difference. So any 2 operations commute. An implication for this reduction process is as follows. The typical procedure that we would use, and the procedure that we've used in all of the other videos that I've made, is in this reduction formula, first we have this 1 over the order of the group. The order is the number of operations in the group, and we see clearly that we have 8 operations, so the order of the group is 8. So we have this 1 over 8. And then we have a series of terms where we multiply the character in the reducible representation times the number of operations in the group, in the class, number of operations in the class, and then multiplied by a character from the character table. Well, we notice here that in every single case there is only one operation in each class. So to save writing, in this particular case, we will not write out this multiplication by 1. If we had more than one operation in a particular class, we would not be able to make this labor-saving device. So if you compare it with the previous videos we've made, you would notice in those videos we have a series of terms that involve the multiplication of 3 numbers. And here we're only going to multiply 2 numbers. The first number is going to be the character from the reducible representation. The second number is the character from the character table for D2H for the appropriate irreducible representation. So, to find out how many A1Gs we have in our reducible representation, we always have this 1 over the order of the group to begin with, so 1 over 8. And then we have a series of terms where we multiply. So first for the first class, we have the character from the reducible representation is a 6. And then the character from the character table is a 1. So we have 6 times 1. Next we have the second character from the reducible representation, which is a 2. And we multiply it by the character from the character table, which is, again, a 1. In any cases where the character is 0, since anything times 0 is 0, we can simply omit these for the time being. We don't need to worry about them. We only need to worry about the non-zero entries. So our next non-zero entry is for the sigma xy, and we see that our character from the reducible representation is a 4. And the character from the character table for D2H is a 1. And then we continue with our character being a 2. Times 1. And then, last but not least, we have the final term, which again is a 2. And we multiply by the character of the character table, which is a 1. And finally, we need to add up all the terms here, and we get a total of 16. 16 divided by 8 gives us 2. So it tells us that there are 2 copies of the irreducible representation A₁G in our reducible representation gamma sigma. Even if I did not have the character table available to me, I know that for the first irreducible representation in any point group, it is the totally symmetric representation, which means that the characters are always 1. So the character in the character table is always going to be all 1s for the very first irreducible representation, which in this case is called A₁G. An important feature to notice is that I am deliberately color-coding the numbers here to show that these first numbers in each term that are red are coming directly from the reducible representation. And we saw how we got those red numbers. The numbers in blue are from the character table, and you will find that either available online or in your physical or inorganic chemistry textbook. But because of the way the derivations are done, the first term, which comes from the reducible representation, will always be the same. It is only the second number, the number that comes from the character table, that changes depending upon the irreducible representation. So as a labor-saving device, once you begin your reduction procedure, you can write down the first number immediately for all of the expressions, because that's not going to change. And also, it's a good way to avoid error. If you write those down first, then you know that they're all exactly the same and you haven't made any errors. So now we're going to put in the values from the character table that are appropriate to the irreducible representation B₁G. So the first character is a 1. The character for here is a 1. Then we have a 1. And then we have a -1 and a -1. So because of the ease of mistaking a minus sign for this little multiplication symbol, I will use a trick here that is common in crystallography. And that is to write a minus with a line over top of it. Almost as a 1 hat type thing. So 1 with a line over top of it. And this is meant to mean -1. It just makes it easier to see the minus sign and not to confuse it with this little multiplication dot. So in the case of B₁G, it's 6 times 1 plus 2 times 1 plus 4 times 1 plus 2 times -1 plus 2 times -1. And that gives us 8 divided by 8. So it tells us that we have 1 B₁G in our reducible representation. Now for the B₂G irreducible representation, we have 6 times 1 plus 2 times minus 1 plus 4 times minus 1 plus 2 times 1 plus 2 times minus 1, which is equal to 0. Note that if you ever get a negative value or you get a fraction, then you have clearly made a mistake. The only possible values, if you apply the formula correctly, are going to be 0 or some positive integer. Then for B₃ᵤ, it's 6 times 1 plus 2 times minus 1 plus 4 times minus 1 plus 2 times minus 1 plus 2 times 1, which gives us that there are no B₃ᵤ's in our reducible representation. The fifth irreducible representation in the group D2H is AU. So here we have 1/8 of 6 times 1 plus 2 times 1 plus 4 times minus 1 plus 2 times minus 1 plus 2 times minus 1, which gives us 0. So there are no AU's. For B₁ᵤ, we have 1/8 of 6 times 1 plus 2 times 1 plus 4 times minus 1 plus 2 times 1 plus 2 times 1, which gives us that there is one B₁ᵤ in the reducible representation. Then for B₂ B₂ we have 1/8 of 6 times 1 plus 2 times minus 1 plus 4 times 1 plus 2 times minus 1 plus 2 times 1, which gives us that we have one copy of B₂ in the reducible representation for sigma bonding in diborane. Now for B₃ᵤ, we have 1/8 of 6 times 1 plus 2 times minus 1 plus 4 times 1 plus 2 times 1 plus 2 times minus 1, which gives us, we have one of these. So in summary, what have we found? Well, we found that we can write the reducible representation for sigma bonding in borane as 2 copies of the Ag irreducible representation plus 1 copy of the B₁ᵤ irreducible representation plus one of the B₁ᵤ's plus a B₂ plus a B₃ᵤ. And one thing to notice, write this more carefully here, obviously that's a U, is that since we started with 6 atomic orbitals on hydrogen, we must end up with 6 molecular group orbitals. And we notice that if we add these up, we have 2 plus 1 plus 1 plus 1 plus 1, we get a total of 6. So that's important to make sure that those numbers agree. If we get different values, that means that we've made an error someplace. So far, we were able to generate a reducible representation for sigma bonding, and then to reduce it to a linear combination of irreducible representations. In our next step, we want to get an idea of what the group orbitals actually look like. First, we're going to see what they look like mathematically. We're going to derive them. And then finally, we are going to see what they look like visually. To develop a mathematical expression for each of the group orbitals, we again have to construct a table. Now we have a table with one column for each symmetry operation. And because of the abelian nature of D2H, it just happens to work out that this table looks exactly the same as the previous table. For most groups, which are not abelian, the tables will look different. So in this case, we have one column for each symmetry operation. Another challenge in diborane from other molecules that we've demonstrated is that each of the hydrogen atoms in diborane are not all symmetrically equivalent, which means that each one, for example, if we had an NMR spectrum, each of these would not give the exact same signal in the exact same place. We would have different chemical shifts because the hydrogens are in different chemical environments. In terms of group theory, we would notice that there is no symmetry operation which will interconvert H1, for example, with H4. H1 and H2 can be swapped by a symmetry operation. So H1 and H2 are symmetrically equivalent. And similarly, H's 3, 4, 5, and 6 can be permuted by a symmetry operation. So those are all equivalent to each other. But H1 and H3, for example, are not. So we want to see what is the effect upon the s orbitals corresponding to each hydrogen atom. So the s orbital corresponding to H1 we're going to call S1. The sigma orbital, the s orbital, corresponding to H3 we're going to call S3 here. So just not to get confused by the difference between H and S. H is for the hydrogen atom itself, and S is for the corresponding s orbital on that particular hydrogen atom. So we need to have two rows because S1 and S3 are not symmetry equivalent. Okay, so let's go. Let's see what happens to S1. Well, under the identity, S1 stays exactly where it was, so it stays as S1. So here we're putting down where the orbital goes under the operation. For the C2 around the z-axis, well, since it's around the same axis, S1 stays at S1 as well. So now we have the y orbital, C2. So the C2 goes around this particular y-axis. So therefore, the rotation will take S1 to S2. Similarly, if we go around the x-axis, which is here, that's going to rotate H1 to H2, so S1 goes to S2. The inversion operation takes S1 to S2. The xy plane is the plane that goes in this direction, so perpendicular to the plane of the whiteboard. So that would reflect H1 to H2, so S1 goes to S2. For the xz plane is the plane of the whiteboard, so S1 stays as S1. And then YZ is this plane coming perpendicular out of the board, going vertically, so that takes H1 into H1, so S1 goes into S1. So next we take a representative orbital of the other sets, S3, and see what happens to it under the various symmetry operations. Well, if we apply the identity, S3 stays exactly where it was, so it stays as X3, because that's what the identity does. Next we have C2Z, so that's around the z-axis going vertically, so that's going to rotate H3 to the position of H5, so S3 goes to S5. Now if we go around the y-axis, that's this particular axis, so that's going to take H3 to H4. That's going to be S4 here. Keep my terminology consistent. Then as far as the x-axis goes, so the x-axis is here, so that's going to rotate H3 to H6, so S3 goes to S6. Next, if we have our center of inversion to this point here, so it takes H3 all the way across to H5, so S3 becomes S5. Now the xy plane is the plane that H3, H4, H5, and H6 are all in. Since they're in that particular plane, S3 will stay as S3. Now for the xz plane, that's the plane of the whiteboard. So that would reflect H3 to H6, so that's S3 to S6. And then for the YZ plane, so that's going to be this particular plane coming out of the board here, that's going to reflect H3 and back to H4 and back on the other side, so that's going to be S4. So here we have a table, and we notice, just to emphasize the fact that we see that none of the entries in the first row is the same as any of the entries in the second row. So this is confirmation that S1 and S3 are not symmetrically equivalent. They are chemically distinct, particularly from the point of view of NMR. And they're also going to be distinct from the point of view of their bonding and their contribution to the group orbitals. To now find a mathematical expression for the group orbitals, we take each case where we had an irreducible representation in our reducible representation that we found before. So we found that there was two AGs. So what we need to do here is to multiply each character that we have in the table by the appropriate character from the character table for D2H, and recall that AG, being the totally symmetric representation, has all ones. And it's a little tricky here because we have two copies of AG, and it's going to turn out that we need to handle the first row and the second row separately. But we multiply character by character, so let's do it for the first row. So we have 1s1 plus 1s1 plus 1s2 plus 1s2, and so on. And we would see that we get 4s1, just kind of show here, we get 4s1 plus 4s2, and we can always reduce the coefficients to lowest terms, and we get s1 plus s2. So that is one of our contributors for AG. We'll see how we have to construct AG at the end, which is a little different than we've done for previous molecules. For the time being, we realize that we have this contribution S1 plus S2. And then similarly, we multiply each of the characters here in this row by the character in the character table. So we have 1s3 plus 1s5 plus 1s4 and so on. So that would give us 2s3 plus 2s4 plus 2s5 plus 2s6, which is s3 plus s4 plus s5 plus s6. So here we have mathematical expressions for the AG orbitals. We have two of them. Now, what isn't clear at this moment, which we're going to leave till the very end, is how this particular contribution interacts with this contribution. That will be a little different than for other molecules that we've done, so we will actually leave how we combine these two together to the very end. But for the time being, this process of taking the characters from this table that we've made and multiplying it by the characters from the irreducible representation, adding them up and then reducing to lowest terms, we will apply to the other irreducible representations. Next, we attempt the B₁ᵤ irreducible representation. And here I've noted the characters from the character table, where this is a 1 and this is a -1. So again, we multiply each character in our table in green times the number in blue, and we add those together. And we notice for the first row that we get a value of 0. So that tells us that S1 and S2 do not contribute to the B₁ᵤ orbital. If we continue now for the second row, we get S3 minus S4 plus S5 minus S6. And each of these will be multiplied by 2, but we're going to speed things up and just reduce that immediately. And we would see that we get S3 minus S4 plus S5 minus S6. So this gives us a mathematical expression for the B₁ᵤ linear combination of group orbitals on hydrogen in diborane. So that's the B₁ᵤ. The next irreducible representation we're going to work with is B₁ⵤ, and I've written down the characters from the character table, where this is a +1 and this one with a line over it is a -1. And we notice now that if we multiply through each of the rows, we end up getting 4s1 minus 4s2, but we can reduce that down immediately to s1 minus s2 for the first row. And then we would notice that for the second row, all these terms will sum to 0. So that tells us for the B₁ⵤ group orbital, it only involves s1 and s2 in the form of s1 minus s2. Next, we have the B₂ irreducible representation with the characters 1 and -1. If we multiply these characters times the characters in green for the first row, that sums up to 0. If we do the same for the second row, we're going to get S3 plus S4 minus S5 minus S6 after we reduce to lowest terms. So this is our mathematical expression for the B₂ linear combination. The sixth and final irreducible representation that we have to work with is B₃, with the characters of a +1 and a -1 shown here. If we multiply the first row terms in green times the values in blue and add them together, they sum to 0, so that tells us that S1 and S2 do not contribute. But then if we multiply the second row and then we reduce to lowest terms, we will get an orbital that looks like S3 minus S4 minus S5 plus S6. With this, we've determined mathematically expressions for all 6 of the group orbitals. The final step is to visualize what these group orbitals look like, and also, very importantly, determine which atomic orbitals on the central boron atoms have the proper symmetry to interact with the group orbitals to form a larger molecular orbital. So that is what we're going to do in the final step. We found that we had expressions for Ag, so we had S1 plus S2, and then we had from the second line S3 plus S4 plus S5 plus S6. How we can interpret these mathematical expressions is as follows. That if they're combined with a positive, with a plus sign, that tells us that the orbitals have the same phase relationship. If there is a minus sign, that tells us that the two expressions connected by the minus sign have opposite phase relationships. So now we notice, we have these two orbitals have the same phase relationship, and these 4 all have the same phase relationship. What we don't know is how the phase relationship of this one corresponds to that one. And it turns out that there's 2 ways that we can do this. So let's kind of show that mathematically, and then we'll see what it looks like graphically. So the first is that this set and this set are in phase agreement with each other. So that would just give us simply S1 plus S2 plus S3 plus S4 plus S5 plus S6. Everyone has exactly the same phase relationship. All would be, say, positive phase at the same time. It works equally well if they're all negative phase at the same time. Just the plus sign tells us they have the same phase. The second possibility, which is distinct, is that while S1 and S2 have the same phase relationship as each other, they have the opposite phase to the group S3 through S6. So what would that look like? Well, that would give us minus S1 minus S2. So since they have the same sign as each other, they have the same phase relationship. But they have a different phase relationship, the opposite one, to S3, S4, S5, and S6. So it turns out that a tricky aspect to finding the molecular orbitals for diborane is that we have 2 different Ag combinations. And the reason why we have this is that we have 2 chemically distinct sets of hydrogen atoms. So they can either be in phase with each other, as in the first combination, or we can have that the one chemically distinct group is out of phase with the other chemically distinct group. So that gives us our minus S1, minus S2, and then these are plus. So all the pluses have the same phase, all the minuses have the same phase. The minus and plus are opposite phase to each other. Now, to make things easier to see, I'm going to draw the molecular orbitals in exactly the same place where I've kept the overall diagram for diborane. So that will say if I erase something, you're to interpret the layout of axes to be exactly the same as it was before. I'm making up for the fact that I am not a very good artist. So let's look at the first Ag combination. So here, all the orbitals have the same phase, and we've already sort of represented them as being open circles. So one way to represent a phase is, for example, an open circle, kind of white in the center, we imagine to be positive phase, and if it's filled in, we consider that to be negative phase. So here, everything has exactly the same phase. So we need to find atomic orbitals on boron that have the proper symmetry to make as many bonding combinations as possible with these 6 hydrogen atoms. Again, remembering that the 2 borons and these 2 hydrogens are in the same plane, and then the other 4 hydrogens are perpendicular. So the proper combination would be to have the 2s orbital on this boron and the 2s orbital on this boron. So they are all in phase. The 2 boron atoms are in phase with each other. That's a bonding combination. Plus they're in phase with all of the neighboring hydrogens, so we have the maximum number of bonding interactions. So this is one of the Ag molecular orbital combinations. Now let's try to construct the second Ag combination. So here S1 and S2 are of opposite phase, so we will demonstrate that by filling them in with the green here. So we'll fill them in with green. So now we need atomic orbitals on boron that have the proper symmetry to maximize the number of bonding combinations. And we've already used the 2s orbital on boron, so we can't use that again. So now we expect that we're going to use the 2p's. So the proper symmetry combination on this boron would have a negative phase towards hydrogens 1 and 2. So since they're all the same phase, that's a bonding interaction. Plus it's going to have the positive phase on this side, so this is a bonding interaction. And a similar construction for the rightmost boron. So its left lobe would have to be negative here. So that's a bonding interaction with the other boron as well as with the hydrogens 1 and hydrogen 2. And then the opposite phase here, remember, because the p orbitals, one lobe has one phase and the other lobe has the opposite phase. So now this is a bonding interaction with the H3 and H6. So this gives us a pictorial representation of the other Ag combination for diborane. So now we try to do the B₁ᵤ, which is S1 minus S2. So pardon my lack of tidiness here. Trying to remove everything else that might be distracting. Since we have S1 minus S2, S1 has a positive coefficient, S2 has a negative coefficient. So that shows us that we have the opposite phases. And notice that the other S3 through S6 do not appear in the expression. So therefore I've erased them from the board because they do not contribute to this particular molecular orbital. So the only 2 that are involved are S1 and S2. So we want to imagine which atomic orbitals on boron have the correct symmetry to interact with this particular group orbital combination. And it turns out the combination has to be one where we have a positive lobe in this direction and a negative lobe in this direction. So we have our positive lobe here and our negative lobe in this direction. And because of the way I've chosen our axes, my blue is kind of running out there. Make our blue a little more intense here. There we go. This is the pz orbitals on the boron atom. So this is the 2pz. So each of the 2pz's of boron are in a bonding combination with each other, and these lobes are all the same phase, so that's a bonding interaction. This are all the same phase, so that's a bonding interaction. And then we notice that we have a node through the molecular orbital that goes through the 2 boron atoms. So this is the B₁ᵤ molecular orbital combination for diborane. Next we have the B₂ combination, which mathematically was S3 plus S4 minus S5 minus S6. So that tells us S3 and S4 have positive phase, S5 and S6 have negative phase. The important thing is that the phases are opposite. So, and recall that using the convention of the wedges coming towards us and the dash going away, that we're to view it as these 2 orbitals are in a plane in front of us, in front of the 2 borons, and these 2 s orbitals are behind the board. So we need to find the particular atomic orbitals on boron that have the proper symmetry. So we notice that because of the phase relationships, we have to have a positive phase in this direction, and a negative phase in that direction. And similarly for this particular boron atom. And because of the convention that we're using, this lobe is coming towards us, this lobe is facing away, so again it's in the xy plane, and it makes these particular p orbitals the 2p's for boron. So notice we can't use any of the boron atomic orbitals more than once. So if it forms a molecular orbital, we can only use it once. So we've already used 2s, here we use 2p, and we've used 2z. 2pz for a combination as well. Notice that S1 and S2 do not contribute to the B₂ And again, here notice that in a line going through the boron atoms, that we go from positive phase through 0 to negative phase, so we have a node, a molecular node through there. Next we have B₃┬, which is mathematically S3 minus S4 minus S5 minus S6. So that tells us that S3 and S6 have positive phase, S4 and S5 have negative phase. So we need to come up with atomic orbitals on boron that have the proper phase relationship to combine here. And one that we see that will do that is we need to have the negative phase here. So in essence, we have p orbital, it's got to be a positive phase here. And similarly, we have a positive phase here and a negative phase in this direction. So here we see we've used the px, 2px orbitals on boron, but we've done it in an anti-bonding combination because, while these are all the same phase relationship, so that's a bonding interaction. These are all positive, so they're a bonding interaction. But between the two borons, we have a negative phase and a positive phase. So we have a node here, a molecular node, even between the two boron atoms. So this makes this interaction antibonding with respect to the borons. I had mentioned previously that we can only use each of the atomic orbitals on boron once. I should be clearer to say that we can only use each combination once as a bonding combination, and then once as the anti-bonding combination. So for any one particular orbital, since it can make both a bonding and an anti-bonding interaction with the other atomic orbitals on the other boron, we have two possibilities for each combination. So here we have the anti-bonding combination for 2px, and for a final orbital, B₁┤, we will see how we're able to use the 2py orbitals, again, this time in an anti-bonding combination to make a bonding molecular orbital. Our final molecular orbital that we're going to visualize here is B₁┤. Mathematically, we have S3 minus S4 plus S5 minus S6. So we see positive, negative phase. So we need to find the appropriate atomic orbitals on boron that have the proper symmetry. So we notice we want to have a bonding interaction. Here on boron we need to have the negative phase for the negative phase on hydrogen. Then the positive phase in this direction for a bonding interaction. Then over on this side we have a positive phase with positive phase, a negative phase with negative phase down here. But notice, relative to each other, these are the 2py orbitals on boron, but now they're the anti-bonding combination. So for any combination of two atomic orbitals, we make both a bonding combination and an anti-bonding combination. And here we have an anti-bonding combination. And notice in this combination that we have a molecular node along this line, and we also have a molecular node along this line. So here we have a molecular orbital that has two nodes. So with that, we've derived all the linear combinations, the group orbitals on hydrogen, and we've constructed the overall molecular orbitals by finding the appropriate 2s or 2p atomic orbitals on boron in the proper bonding or anti-bonding combination to make the molecular orbitals. Just as a final note, some things which we did not do in this particular video is I did not bother to find the normalization constants for the molecular orbitals. That is a slightly more advanced topic. It's not terribly important as far as being able to visualize the phase relationships or the overall nature of the molecular orbitals. To see how that's done, you can check some of my other videos. It's not terribly difficult to do. As always, I thank you very, very much for your kind attention through what has been a very long video. As always, have a good one.